Hello, good welcome. Sorry for the slightly late start. So good afternoon, everybody. Welcome to another CERN Colloquium, which today is all about the most comprehensive optical astronomical sky survey ever undertaken, modestly titled today as the greatest movie of all time. I'm delighted to introduce our speaker today, astrophysicist Zeljko Ivezic. Apologies for my pronunciation. He received his PhD in physics from the University of Kentucky in 1995, and then moved to Princeton University as a postdoc to work on the Sloan Digital Sky Survey, the groundbreaking precursor to the Vera Rubin Observatory. In 2004, he took up a professorship at the University of Washington, and until recently, and was director of construction for the Vera Rubin Observatory until very recently, and is now a project lead for the LSST project. You will learn about the difference between LSST, Rubin, and other terminology during the presentation. He has co-authored over 250 scientific papers and has the high honor of having an asteroid named after him, which was discovered by the Sloan Digital Sky Survey in 1998. A very warm welcome to you, and the floor is yours to tell us about the greatest movie of all time.
Thank you, Matthew. Thank you. Thank you all for coming today and spending time in this room instead of beautiful sunny day outside. So as Matthew said, I need to clarify nomenclature. Vera Rubin Observatory is the observatory with all supporting systems. It's an institution that has people working for it. The first project that it will undertake will take 10 years. It will be a survey of the night sky, and that's called the Legacy Survey of Space and Time. So one is observatory, the other one is project it will undertake, an experiment in the language that you may be more familiar with. It is a bit confusing because the first name of the Rubin Observatory was Large Synoptic Survey Telescope, which has the same acronym, LSST, and that's the source of a lot of confusion. So there is observatory, and there is the first project that we will undertake. This is drone video of the observatory made last year. The observatory is finished, and we started the Legacy Survey of Space and Time just 2 days ago. After 20 years of first a decade of design and endless reviews and a decade of construction, we finished last year, spent a few more months fine-tuning the observatory, and finally we met all the specifications for the image quality, for the quantity of images we can make per night, calibration, etc. And we declared 2 days ago that the 10-year program called LSST started. So it will be transformative for astronomy, and I hope by the end of the presentation you will believe this blank statement. When I said the greatest movie of all time, I did not speak in Hollywood terms. I simply looked at the data volume and the amount of data we will collect. It will be about 60 petabytes of data, and if you wanted to look at every image adjusted to human eye resolution with 30 frames per second, then it would take you 11 months to see every single image we will obtain. That's why it's the greatest movie, the largest movie of all time. So what is special about this observatory? It was designed to have the largest ever field of view for 8-meter class telescope. We'll see later why, but first let's see the characteristics of the observatory. Typically, large astronomical telescopes can see a field of view on the sky much smaller than the full moon. And with this field of view, you can fit 50 full moon circles inside that field of view. This outline shows our individual sensors, about 200 of them. Each one is 16 megapixels for the total count of 3,200 megapixels. So we can scan the sky to some given fiducial sensitivity 100 times faster than any large telescope. So the project that I will describe, LSST, that will take 10 years with this observatory, it would have taken 1,000 years with any other large telescope. So it's impossible. That is why we needed to build a new observatory. Why do we want to have such a large field of view? That is because we want to survey the entire sky over and over. And if you look at half sky, we can see from Chile, that's about 2,000 circles. And so each of these circles will contain about 10 million galaxies to our sensitivity limit. We will have about 20 billion galaxies in the sample and a similar number of stars. For the first time, astronomers will have cataloged more celestial objects than there are living people on Earth. So literally, you could name a star and a galaxy after every one on planet Earth, including you. If you're not an optical astronomer, just to illustrate for you the difference between current state-of-the-art for the large-scale digital color survey, like SDSS. In astronomy speak, SDSS goes to 22nd magnitude. If you go to 27th magnitude, like LSST, which in physics speak, it's 100 times better sensitivity, then at this part of the sky, this is teeny tiny part of the sky, 1/10 of the full moon. Then once you increase sensitivity 100 times, you get this image. So it's huge difference. Oh, sorry. So if I go back and forth, you can see many more objects because the more sensitive you are, the fainter objects you see, and counts of celestial objects increase exponentially, literally exponentially, the more sensitive your survey is. And so in order to get tens of billions of objects, you need to go wide across the whole sky, and you need to go deep to low sensitivity levels. And just as a comparison, on the right, you can see this gray outline of our field of view. This one red square in the bottom left, that's 1 CCD, and this image is this teeny tiny cyan rectangle. Now look at this image and appreciate all the beauty and richness of objects, of colors, of counts of objects. And see how big is our large field of view. Now imagine the full field of view packed with 10 million objects. Now you cannot see that. Another difficulty with large field of view is that you have 3,200 megapixels. It is hard to process it, and you can never see the whole image. Your eyes are not good enough. Human eyes do not have enough resolution elements to see every detail in this image. Basically, what your eyes can see is what you get from high-definition TV. You don't need better TV if you already bought high-definition TV, because your eyes will never know. And your eyes basically can see half of our CCD. So in order to display the whole image from this camera, so that human eye can appreciate all the detail, you would need 400 televisions, like basketball court paved with televisions. That's impractical. But we can play with software. I'll show you later how you can explore the whole image. So why do we want to scan the whole sky? We have hundreds of science drivers. I will touch upon only a couple of them today. The one that is probably the most fundamental, most important, and probably most relevant to physics audience like you today is the accelerated expansion of the universe and dark energy and modified gravity theories. How can we tell them apart? Hubble discovered expansion of the universe 100 years ago, and for almost a century, we all, physicists, astronomers, we thought that that expansion was supposed to decelerate, to slow down. We didn't know if we would asymptotically expand forever or maybe stop and go into a big crunch like half a century ago. But nobody thought that acceleration would be present. Even we had something that in cosmology is not popular anymore. It was called deceleration parameter. That is how strong theoretical paradigm was. Then, about 20 years ago, it was discovered that the universe is expanding and accelerating at it. Since about redshift of 1, acceleration, the expansion is becoming faster. One way to explain all the astronomical observations without pretty much no strong conflict, and I'm not now referring to the most recent Hubble tension and DESI results, but most of the astronomical observations over the last few decades, we can explain by adding one term to the equations termed dark energy. It's dark, but it provides explanation for the accelerated expansion of the universe. The bad thing is we have absolutely no clue from theoretical physics what it could be. But the conclusion that you need to add a term is based on an assumption that we barely state explicitly, that we believe the general theory of relativity, our theory of gravity, is correct. You don't have to have dark energy if you admit that maybe general theory of relativity needs modifications. And indeed, there are hundreds of papers already published that show different ways of how to do it, how to modify GR a little bit and explain all the astronomical observations. So we have two hypotheses. Even we have new mysterious fluid that accelerates the expansion of the universe, or Einstein was wrong and we need to modify GR. Which one is less wrong? We don't know because our data are not good enough. And most of these data that will tell us about these two hypotheses are astronomical data sets. And so in the context of astronomy, what we can do is to measure supernovae, for example, to measure directly expansion of the universe. And even better probes are galaxies. And so you can do simulations and show that you need billions of galaxies. Now, this image shows a cross-section of the three-dimensional volume explored by SDSS. Think of a pomegranate. You cut it in half, and you look at the structure from the seeds. The most important point here is that this structure, these little dots, are all individual galaxies. It's not homogeneous. It is strongly structured. And by measuring this structure, by looking at the power spectrum, we can connect to cosmological parameters. But there are not enough galaxies in this range explored by SDSS in order to get billions of galaxies. And you need billions of galaxies to get to percent-level precision so that you can distinguish predictions between dark energy and modified gravity. You need to measure expansion of the universe simultaneously with the growth of structure in the universe. And so to do that, you need to map galaxies in this bigger circle. But the further out you go, the fainter galaxies are, and you need bigger telescope. And that's why we couldn't do it with these existing telescopes. We needed new 8-meter class telescope that, unlike other 8-meter class telescopes, at the same time will have this giant field of view, and then we want to map about 20 billion galaxies. We want to measure their large-scale structure. In addition to measuring just distribution of those dots, where each dot is a galaxy, we will also measure the shapes of galaxies. And by measuring shapes of many galaxies and averaging, we can measure their distortion due to dark matter. And then we can measure dark sector in general, and we can combine with acceleration to constrain cosmological models. So by measuring out to redshift of 1 or so, we can do tomography of dark matter structure that also participates in cosmological equations. So basically, we will have a movie of the growth of structure measured through power spectrum, measured through weak lensing, measured through clusters of galaxies, combined with the CMB measurements and supernovae to have one overall constraint, simultaneous constraint on the growth of structure in the universe and the accelerated expansion. And the belief is based on simulations that with about 5 years to 7 years of LSST data, we will be at the threshold where we can start distinguishing those two major hypotheses for why expansion is accelerating. Then there are hundreds of other science cases going through the Milky Way structure, evolution of galaxies and such that I will skip completely. And let me just finish close to home with the studies of Milky Way, of solar system structure. As we get 1,000 observations over 10 years in order to study supernovae and other time phenomena, at the same time we'll get asteroids essentially for free. In last 2 centuries, of the order 1 million asteroids were discovered by everyone. And in year 1, we will double this number. We will end up with about 5 million asteroids in our solar system in just a few years. It will be completely transformational for solar system science. And asteroids are important because they encode the history of how solar system formed and how it evolved. And among those asteroids, 5 million, there will be about 100,000 that cross Earth's orbit. That doesn't mean they will hit Earth, because you have to be at the same place at the same time. But we will measure their orbits, and if there is any, we will be able to alert, and we can then plan what to do about it. So the observatory is sited in Chile, next to Gemini South Telescope, another US public telescope. Then these dashed lines are fiber optic cables that send data, each of these images of 6 gigabyte image that we get every 40 seconds. It's shipped within a second or so to California, to SLAC laboratory that you probably know about, next to Stanford. They are our principal data processing center. And then soon afterwards, data are also shipped, all the data, to Lyon and to Edinburgh. So we'll have 4 copies of data around the world, and then the 2 centers will help US center to process all the data. Here is the telescope when it was assembled, constructed and assembled in Spain, which constructed telescope, and then it was disassembled, shipped to Chile, and reassembled in the observatory. It looks unusual because it's very squat. It's designed to move very fast. It needs to slew and settle in 5 seconds. Because our nominal exposure time is 30 seconds, so to have high efficiency of using observing time, you have to slew in short time compared to 30 seconds. And here is illustration. This video is not sped up. This is real speed. This is the fastest large telescope that there is. If you've never observed a large telescope, it takes minutes to go from this direction to 180 degrees away. Many minutes, often, and we can do it in a few tenths of seconds. 5 seconds to go from one position to the next. Another technological marvel that enabled LSST is this camera. It was designed and constructed at US DOE labs, with the principal lab being SLAC. That's where it was assembled, constructed, assembled in their clean room. It's a giant camera. This silhouette was from Nadine, former project manager, Nadine Kurita of the camera team. She realized she was exactly the same height as the diameter of the entrance pupil. It is the largest camera ever constructed. Here is a real photograph from the clean room at SLAC. The light comes from the left. You can see this metal cover to protect the lens. And then roughly halfway through the black cylinder is the focal plane with the sensors. And then electronics and cooling system is in the back. Here is another photo from the back. We have 200 sensors. In order to enable readouts of 2 seconds, each sensor is segmented into 16 segments, and then these 16 times 200 is about 3,000 channels that we have to transmit outside of the camera. We did have some child diseases when it was assembled, some vacuum leaks and such, but it's all now under control, and the camera is operating. Here is the glorious team from Stanford, from SLAC and Stanford, physicists mostly, some few garden variety astronomers to help them, who constructed the camera. You can see in the back the entrance pupil. If you look carefully, you can see 2 colors. We have 2 types of CCDs, because not a single vendor could deliver them all, so we had 2 vendors. But the difference in QE and overall transmissivity is small compared to the changes in atmospheric transmissivity as you move from zenith to 45 degrees away, which we have to calibrate anyway. So the fact that we have 2 different types of CCDs, it's not a big deal. Might be even a boon, because at some point in the future, we can split the data by CCD and ask, do we get the same cosmology, as a great check on systematics. This is the lens you couldn't see that was covered with that metal lid. So if you remember your kindergarten stories, the largest lens was Yerkes telescope next to Chicago, 1.1 meter or so. This is now the largest lens ever produced, 1.6 meters, also already in the Guinness Book of Records. And here is how the focal plane was designed. Each little blue square is one 16-megapixel CCD. And each red square is one raft or individual tower that has 9 CCDs and electronics underneath, and they are completely modular, replaceable, one by the other. And that is the focal plane fully assembled with all the CCDs, about 189 science sensors, and then 12 more for controlling focus and optical wavefront. This is one of the first images with that camera. It's a pupil image from the lab of an old photograph of Vera Rubin. Observatory was renamed a few years back after Vera Rubin. She is famous for providing the first convincing evidence for dark matter in spiral galaxies. Although there was some evidence for dark matter prior to her work, it was mostly thermodynamical, and there were ways out of the observations without postulating dark matter. But with her dynamical kinematic measurements, there was no way out of conclusion that there is something that produces gravity that we cannot see. She was also very famous as an advocate for diversity in astronomy and science in general. In addition to our observatory, she also got US quota last year. She's on the newest US quota. So we had a great year. After 20 years of building the observatory, the first decade starting in 2004 was design, optimization, and endless reviews. We started federal construction in 2014. We were delayed by a couple of years by COVID, and finally completed the observatory last year. It took us about half a year to fine-tune it. We have about 50 degrees of freedom to control in our optical train, so we had to spend some time to get all the lookup tables and such, you can imagine. But it all converged in early April. Then we got 2 months' worth of data to demonstrate that it's all meeting the specs, and we declared a couple of days ago that we started. So let me tell you a little bit about early science and show you some data. This is what we obtained about a year ago for our press conference in DC to demonstrate that the observatory was completed. We spent a few weeks getting more data. This is a beautiful image. It's very deep, goes to 27th magnitude. You can see spiral galaxies, elliptical merging galaxies, lots of stars in the foreground of Milky Way. It is just beautiful. It bursts with detail, with beauty. But it's not the full image we got. As I already told you, your eyes are not good enough. So this image is only this orange rectangle, and the full image is this green outline. So let me now, instead of going out to basketball court, let me show you a little bit of zoom-in, zoom-out game with a little video clip that will let you appreciate how much detail there is in this giant image. In just one image, how much information there is. So this was zoomed in. Now we see some elliptical galaxies, spiral galaxies. We zoom out and zoom out and zoom out. Then we pick another point. And then we zoom in. Beautiful elliptical galaxy. These are the same two spiral galaxies we saw before. But now you can appreciate how huge is just one image from this amazing camera and amazing telescope. So this is basically 2 of our images on the sky. We need 2,000 to cover half the sky. So amazing data set. Again, for non-optical astronomers, just to appreciate the progress that this technology gave us, this was done by SDSS 2 decades ago. And you can see 3 galaxies that seem to be minding their own business. Like they don't talk to each other. They don't know about each other. They are sufficiently far away. But now with much more sensitive data, with sensitivity going up by a factor of 100, thanks to technological development over the last 2 decades, this is what we got with Rubin. So here, they don't know about each other. Here, it's obvious that these galaxies are interacting, that there is a lot of intergalactic material, that the force of gravity is steering them apart. So there is a lot of detail. This is just an illustration, but shows you how far astronomy got over the last 2 decades. Another aspect of the data is that we will have time direction resolved. And to illustrate what you can do with time, you can look at supernovae. Here is an example with asteroids. Asteroids in our solar system move relative to the static background of stars and galaxies. And so in just a few nights of data, we discovered about 11,000 new asteroids, because just we have giant field of view, you have so many observations, and they just pop up effortlessly. And finally, we are designed to look after billions, tens of billions of objects. We did not design the survey to look for pretty objects. But when you look everywhere, then you see pretty things too. And so here is one pretty thing. This is nebula relatively close to our solar system. It's in the disk of Milky Way. These are giant clouds of gas and dust where baby stars are born. Indeed, in the bottom right, you can see this whitish area. That's a bunch of siblings that were born just a few million years ago. So here, too, it would take other big telescope. Oopsie. Other big telescope would have taken a year of observing that region on the sky, and with this camera, we managed to observe it in just a few nights. Something's happening. Maybe I have too many Python notebooks open. It's glitchy, but the same idea. You scan, you zoom in, and then you show all the great beauty. Now, if you go back in, you can see amazing detail. If you're not an astronomer, you may think that these black regions, that they are holes in the sky. They are not holes in the sky. They are giant clouds of dust between the stars and us that completely obscures the light, and it appears visually as you had a hole in the sky. So these are Trifid and Lagoon nebulae. Let me see if I can recover. That doesn't look good, does it? Okay. Patience is a virtue, right? Give me a second, I'll be back in a moment. All right, that's where we stop. Sorry about that. Does it look good? It looks good. So that was a great year for us. We made it as the best science image of the last year. We got huge coverage in newspapers and so on. It was great. But what you can't tell with your eyes, that in those images, the resolution was about 20% worse than our requirements. So we had to spend 5-6 months fine-tuning things to enable science at the level that we were designed for. As I said earlier, there are many science teams. They come in 4 general areas based on deep data and time-resolved data. The way we are going to get this data set, and an important aspect of LSST data set is that one data set will serve those hundreds of science cases. So we optimize the survey, and then everyone, people interested in asteroids, in stars, in the Milky Way, galaxy evolution, quasars, supernovae, weak lensing, galaxies, cosmology, they all use the same data set that is also processed to great extent by the observatory. The way we optimize it is we want to maximize effective observing time. That depends on where the moon is, what phase it is in, how much we covered. You don't want to paint yourself in the corner. We want uniform coverage. We have to make a decision about 1,000 times per night where to point and which filter to use, and that's too much for humans. So what we do is we just run, essentially, you would call it today AI to be fancy, but it's basically cost function optimization. There is a lot of stuff for scientists that you can utilize to get yourself or your students up to speed if you want to work with this data. I cannot go through all the details, but I'll just give you some highlights. We already had data preview 1, which was teeny tiny amount of data, just to learn how to use our data formats and such. There were maybe 24 science papers based on it, but tiny set. That was based on engineering camera. But in few weeks from now, we are releasing a giant data set, 3,000 square degrees of sky to depth of LSST. That's basically 1% of LSST already there, and that's now much better than any other survey or comparable. Let's say dark energy survey is similar. In 2 years from now, we will have data release 1, and that will be about 10% of LSST. And an important aspect of, is that me doing something? Huh? Maybe someone needs to mute on Zoom or something. And we also have alert signs. So one of interesting unplanned discoveries was, not truly discovery, it was discovered by Atlas survey, but there was this very intriguing object, only third discovered so far, that comes from outside the solar system, goes around the sun and leaves, called interstellar object. They were extremely popular over the last few years because a certain colleague from Harvard thinks they are spacecrafts with aliens. But we managed to observe this one just by pure luck. We were getting this PR data in about 1,000th of the sky that we can see, and this object just happened to be at that time in that 1,000th of the sky. So we got beautiful data set. We showed it's a comet, it's resolved, there are no aliens waving at us and such. That was great paper. That's the first paper that came out, first refereed science paper from this giant camera. There was another asteroid paper on light curves that came around the same time. I mentioned alerts. Alerts is very unique way to contribute not to science we want to do, but to multi-messenger astronomy in general and to connect with many other projects. So what this is trying to show is a system where we take any new image that we get, and in this slide it's called image 2. There are 2 examples, top and bottom row, and we take then the average of all the previous images on that part of the sky, and we subtract the 2 images, pixel by pixel. In reality, it's not so simple, because when you observe at different directions, atmosphere acts as refractor, and then you get different shifts of objects depending on their color. When you observe, you also have different resolution because atmosphere changes, and you also have different background brightness because you are observing a different night. So it is much more complicated than just take the 2 arrays and subtract, but it can be done, and in a statistically nearly optimal way. So that's what we do. And so in the first row, you can see 2 images that are subtracted, and nothing changed on the sky. What you get is noise due to the background. Static objects subtract out. But in the bottom row example, you can see in image 2, there was a new object. And so then we have an object in the difference image. And of course, then we again run Object Finder. We measure position, brightness, etc. of that object, its shape. And we package this into a software packet we call Alert. And within 60 seconds of closing the shutter in Chile, all that happens, image travels to California, we subtract it, we measure it, we package it, and it goes to 7 so-called brokers around the world, where the full stream goes, and those brokers then, they're like software platforms, they then provide filters to users, and so you may be interested in supernovae or in tidal disruption events when star goes around black hole and gets swallowed, or you want to look for supernovae, whatever changes on the sky, you can now filter this stream and deploy other telescopes. That's the idea of that alert stream. The best alert stream prior to Rubin was Zwicky transient facility run at Caltech. They had close to 1 million such alerts per night. And we think we'll get close to 10 million alerts per night. So about an order of magnitude increase in throughput of these alerts. We started this February. We were very happy. We worked on that software pipeline for about a decade. And there are already papers coming out, even though so far it's a tiny stream compared to where we will be a year from now when we have full sky coverage. It shows that all this complicated machinery is working very smoothly, and there are even examples of where new data, new spectra were obtained for objects where no human intervention happened. We automatically shipped those images to California. sent alerts to brokers, and then other software picked up those alerts, filtered them, deployed robotic telescopes to go and get spectra, and so then we got spectra of new objects that appeared in the sky with absolutely no human intervention. That's exciting, maybe scary, we'll see. Then with these alerts, we are also enabling multi-messenger astronomy going all the way from high electromagnetic energies all the way to neutrinos from ice cube. And in particular, we will allow for target of opportunity observations for gravitational wave triggers coming from LIGO and related observatories. So here you can see the wavelength or energy coverage for some major high-energy missions like Cherenkov Telescope Array, Fermi, SWIFT, and IceCube for neutrinos. So we will get millions of transients generated each night, and then you can go and cross-correlate that with triggers from other observatories. And it doesn't have to be even highly significant detections by other observatories. You could now take hypothetically, optical characteristics of something, and then you match with some other observatory that doesn't have significant detection. But if you have thousands or hundreds of thousands of such candidates, and you are really selecting them by something physical, you will pick up signal. We already know that from previous examples where we combine optical surveys with radio data, and you take quasars from optical wavelengths that are not detected in radio, but then you take 1,000 quasars, and you take radio image for each of them, and you add those radio images, and boom, you get strong signal by coaddition, statistical coaddition. So we'll play these games with this data too. As I said, we will use 3% of observing time, up to 3% for target of opportunity observations will respond to triggers from LIGO and friends and from IceCube. And Rubin is especially well suited for that because those triggers have large astrometric uncertainties, many degrees. And because we have 10 square degree field of view, then it is a very good instrument to find optical counterparts. And so let me just show you a few slides about what's coming up in a few weeks. So this will be about 50,000 images that we obtained during commissioning period. This shows southern celestial hemisphere that we see from Chile. The color means how many observations we got. We almost observed the entire sky at least once that we can see from Chile. But to produce high-quality coated images without gaps, we need 5 to 6 observations in each band. And so we knew 5 months ago we couldn't cover the whole sky. So we chose that yellow area, which is aligned with the ecliptic. So we got many asteroids too. On that yellow area, we have enough observations to produce very deep coated images. It's about 3,000 square degrees, a little bit less, more than 1/10 of what we ultimately will produce. So this is where we have coated maps. And then we have few deep fields. These teeny tiny yellow dots are places chosen on the sky where we will have about 10 times more data than in the rest of the sky. So these are like these corner cases where we explore other parameter case. Like, for example, EDFS is Euclid Deep Field South. We have agreement with Euclid that those 20 square degrees will observe to that and try to explore synergies between their high angular resolution data and our very deep multicolor optical data. There are many other examples that I will skip over. Here is few the images from that upcoming data set. This is globular cluster in our galaxy. Next one is high galactic latitude. So there are still stars in the Milky Way, but you can now see these beautiful external galaxies. You can see these vivid colors. And this is not just pretty, this is information. We use these colors to get distances to these objects. For galaxies, of course, this is photometric redshift. Because of redshifts that change color of galaxies, by measuring accurately galaxy colors, you can get their distances to within few percent. And similar we can do with stars. So when we run our object detection on this image, each individual object is recognized by algorithm as an individual object. It gets its postage stamp. We know its properties. And now we can play God. We can say, move the stars away, or move the galaxies away. And then you can say, I only want them in this slice. And so let me entertain you with 2 short videos that show how that happens. So here we look at galaxies. We say we don't care about stars. There are forests, trees in front of us. Move stars out. There are no stars here. And now we take a running window in redshift, and we move, and as we go further and further, some galaxies fall out, some galaxies come in that box. And so now as you go further out, you can pick up with your eyes. You can pick up galaxy clusters. You can tell how galaxies on average become redder. So you can do cosmology with your eyes. And that goes to redshift of about 1.5, which is almost half the age of the universe. And that's just with normal galaxies that behave this way. Now, if you're interested in stars, you can say, I don't care about galaxies. I don't care about cosmologists. I want to look at stars in the Milky Way. And this is now stars ordered by distance from us. You can see lots of bright blue stars and faint red stars. That's, of course, luminosity function. That's HR sequence, HR diagram, main sequence. And then first, fewer and fewer stars appear. That's because you're getting out of the disk where exponential counts cause the counts to go down. Once you hit halo, where the law is 1 over r cubed, you can show that then the number of stars per magnitude stays constant, and that's what you can see with your eyes. And distance modulus of 20 is roughly 100 kiloparsecs, the edge of our galaxy. And then I pushed it further, and then eventually we will see contamination by galaxies that we misclassified as stars, because our classification is still pedestrian. It's not fully Bayesian. We are not using priors, but that will be done with the next data release. All right, and a few more slides. I want to conclude in this fine auditorium where I'm sure there are many people who love machine learning and AI and big data sets. I don't want to go into details, but I just want to illustrate for you how beautiful data set this will be if you are interested in machine learning and developing such methods. So every time we look at our objects, about 40 billion of them, we measure dozens of parameters, but for the sake of argument, let's say we measure 10. Position, color, shape parameters, and so on. We measure 10, and we'll do it about 1,000 times. So for each object, we will have of the order 10,000 numbers in database. So that is a 10,000 dimensional space. And that 10,000 dimensional space will be populated by about 40 billion points in that 10,000 dimensional space. And what you want to do is not much different than what we are already doing today, which is basically clustering or unsupervised classification. It is supervised classification with training samples. And once you quantify what's normal, then you can look for abnormal. You can look for outliers or whatever you call them in your domain. And that's what we want to do with this data set too, except that most of our methods today scale with n squared or n cubed. Only a few scale with n log n. But to be efficient in this game, you need to take every method and think about how to go to n log n, or otherwise 10 billion objects will kill you. Your code, at least, just like my laptop almost died. And so that is the message I'm leaving with you guys who like that. This is a fantastic data set for exploring such methodological advances, and I would be happy to talk to you after the talk about many methods that are already being used that were developed over the last decade or so with this problem in mind. It's a rich field for development. So to end, I thank you again. I think this is first Rubin talk at CERN. Thank you very much, Matthew, for the invitation. Thanks for our Rubin team. And I'll stop here, and I would be happy to answer your questions.
Thank you, Zeljko. This was really, the clarity of the talk and the beauty of the images really made this a fantastic feast of astrophysics and astronomy. Questions? Yes.
Coming back to the fundamental question of the acceleration of the expansion, how much do you expect to improve the data on supernova at redshifts of order 1, on which the conclusion of an accelerating
redshift? I missed redshift. You said supernovae at redshift what?
Order of magnitude of
or
one.
order of 1. Yes, we will have few million supernovae, and then exact number depends on how stringent you are on your requirements for your sample. But the numbers will be much larger. And if you look at existing samples and you ask what is the leading source of error, it's a systematic error due to photometric calibration. And we went to extra lengths about calibrating our system. Unlike typical astronomical observations, we will have direct throughput measurements for our data. And when we calibrate, we will give you throughput function. We will calibrate assuming we look at stars. But if you later have supernova, you can then undo the correction, so-called color correction, even though we are doing the full integral. You can undo that, and you can then convolve with SCD of a supernova, and you can go down to systematic errors from about 1% to 1/10 of it or so. So it will be not much larger, not so much that not only that it will be much larger sample by factors of 100 to 1,000, but the limiting systematic error will go down by factor of few, if not 10.
So there is no question that this is going to be extremely important.
Absolutely, absolutely. I did not mention them much today, but yes, supernova are one of our 4 major cosmological probes. Out of 5, 4 you can do in optical plus CMB. So supernovae we will do, weak lensing we will do, large-scale distribution of galaxies we will do, and clusters of galaxies we will do. And then we'll combine with CMB, with Planck, and everything else. So yes, it will be transformative.
I should also say, for anyone on Zoom, and there's lots of
There is one question here.
Oh, yes, indeed. Just to let people know on Zoom, you can submit questions just via the chat, and I'll try and pick them up. Yes. So a question here, yeah.
First of all, thank you for the talk. It was very, very interesting.
Thank you.
And so I can imagine that at the resolution we are at right now, atmospheric effects become more significant. So,
could you just come closer to the
sorry,
microphone?
yes. So I can imagine that at the resolution we are now, atmospheric effects might become more significant than before. So are they limiting to the resolution already, or is it more like technical limits so far? And also could maybe as a byproduct actually one gather information about the, well, changes in atmospheric chemistry, for example, as a byproduct from the data?
Yes, so first the resolution. The image resolution that we have as a ground-based observatory is dominated by atmospheric turbulence. There is contribution from the system too. It's about, after you edit in quadrature, it's about 10%. So if we had perfect system, then it would be 10% better. So it's dominated by the atmosphere. We are Nyquist sampled with our pixels. So effectively, we don't have pixels. You can shift and sag and rotate without loss of information. So it's really the atmosphere that is killing us. Now, if we didn't have atmosphere, we couldn't breathe, so you wouldn't have data anyway. So I think it's a good trade-off. Now, for chemistry, did you mean chemistry of stars or of galaxies?
Actually, I meant the other way around. I come halfway from an atmospheric physics background, so I can imagine that maybe as a byproduct, just by how the filtering of the data must change over time, one could actually gather some new information about the atmospheric chemistry. Just because
you mean at Earth's atmosphere?
Exactly.
Got it. Yes, excellent question. We will have beautiful data because you can fit the transmissivity of Earth's atmosphere using 6 templates. So you have ozone, you have this and that, oxygen, so on. And so basically you have 6 known curves that you can compute at arbitrary, essentially, wavelength. At wavelength resolution much higher than that is relevant here. So it's like infinite. Then what you need to know is 6 coefficients that multiply these 6 templates. You add them together and you get atmospheric transmissivity. And that we will constrain with our data. We will have enough auxiliary measurements. I didn't mention our calibration telescope that will have spectra of stars. So for each observation, for each 40-second observation, we will give you these 6 numbers. And you will be able then to study one night maybe oxygen was going up and down. Another night, precipitable water vapor was going up and down. All kinds of fun stuff that you can do with it, and that will be all available, yes. Thank you for the question. Excellent question.
Thank you so much.
Question here. Yeah, and then you. Yeah.
Hi, thank you so much for this talk. It was really, really interesting. I had a question about satellites. So like you mentioned, it's going to be a 10-year-long program, and I imagine as we go into more of an advanced age in terms of networking, there are orders of magnitude more satellites coming in, which are going to be affecting and polluting the space, so to say. How will that affect the data? Like, do you imagine that as we move ahead, it might lower the resolution of the collected data, or how are you planning on solving that?
Thank you. Excellent question. I was hoping someone would ask that, and I didn't add slides. So, yes, Musk started Starlinks with SpaceX, and originally it was consternation. They were so bright. Then we approached them, and to their credit, they were very responsive. We established collaboration directly with SpaceX. Elon Musk supported this idea to make satellites as faint as possible. They invested into development of new coatings that will have lower reflectivity in optical near infrared where we care, but still be transmittive in microwaves where they care. So that was all great collaboration, and they decreased the brightness by a factor of 6, which was now good for us because it went below our saturation limit. It was good for everyone because it just went from being visible by naked eye to being invisible to humans by naked eye. So all good. But then they realized that they want bigger satellites, so they made them bigger, so now they diminished the previous gain. Now, what will happen with our data? So what happens depends on how bright the satellites are and how many of them you have. These are the two most important characteristics. We did simulations with 50,000 a couple of years ago. That's what they had from FAA as permits to launch them. With 50,000 satellites, the net effect is that when we take those streaks through our images and we count the area that will be covered with streaks down to some noise level, we will lose about 0.2% of pixels, just as if they were in interchip gaps. It's comparable to interchip gaps, so it's nuisance. We had to develop software to treat it. It's not catastrophe. Now it is also true that just recently they got permits to launch million satellites. People in the field say over beer that they are unlikely to launch million. They're basically trying to get other people not to launch. But if they launch million, that would be 20 times more, so then it would be 4% of our pixels lost, which is now becoming unpleasant, very unpleasant. And there are some other nonlinear effects like crosstalk and some systematics in cosmology and so on, that now it's not still catastrophe, but it's hurting. And what to do about it, we don't know yet. The entire astronomical community is united around the world. There are major committees, both in Europe and particularly in the United States, that are now trying to talk with governments, with UN, what's left of it, and so on. So we are trying to fight back, but nobody can predict what will happen.
Terrible irony there, isn't there? As we advance technologically, we shut off our view to the universe.
Exactly.
Question there.
So thank you for a nice talk. I believe that LSST will also give a limit from cosmology on some of neutrino masses. And right now, the mass limit that comes from cosmology is limited. What interests people is whether the neutrinos are inverted hierarchy or normal hierarchy that leads into neutrinoless double beta decay. Juno has given some limit towards normal hierarchy, but it is still 2 point some odd sigma. So when do you think a good result, which says less than 50 MeV can come from LSST? So that was the first question. And would it be making a statement on diffused supernova neutrinos? Because recently at Neutrino 2026, Super K experiment had a 2.6 sigma significance. But again, as you know, it needs to be better, but it will take another few thousand days to go to 3.5 sigma or something, which is a very long time. So would LSST be making a statement on that?
So we get to say something about neutrinos because we measure power spectrum of the large-scale distribution of galaxies. And with 10 years of data, our experts predict we will be able to answer this question about whether it's inverted hierarchy or not. Now, off my feet, I cannot scale it back and tell you in 2 years or 3 years or 4 years we'll be there, but as soon as we have entire sky covered with galaxies, say 2 years from now after we have 10% of data, we will definitely be able to measure the power spectrum of the large-scale distribution of galaxies, and that will give us some constraint on neutrinos. I forget now exact number for the error, but it's you can find the papers, actually. Now that you mention it, this link, ls.st, LOP stands for LSST overview paper. That number is there. There is a little section about neutrinos. So just go there and you'll find the number. Now I cannot recall it.
Question up there.
Thank you for the talk. My question is, I know that you've just started taking data. Do you foresee hardware upgrades to the observatory during the 10-year period, or is it the case?
I'm sorry, can you just come a little bit closer?
Sorry, do you foresee hardware upgrades to the observatory over the course of the survey?
There will be certainly upgrades. We have a lot of subsystems, and some of them, because it took longer to finish, there already some of them are failing, like some cooling systems and so on. We are planning for upgrades. We do have a spare raft for the camera. Unfortunately, originally we thought it would take us 2 months to replace the raft. Now we think it will take longer, so we could have some serious downtime if something happens. We would not stop observing if 1 or 2 CCDs die, but for a full raft, we might stop and replace. Now, for the telescope itself, there are also subsystems could go bad. So we do have a very detailed maintenance program, and every year, if I remember correctly, we plan for, I think, 5 weeks of scheduled downtime. And then statistically, when we model the survey, we assume few more weeks of unplanned downtime due to some problems. So yeah, we certainly plan to upgrade the system as we go.
What was the major technological leap that took us from Sloan to LSST? I mean, was it the chips? Was it the lenses altogether? What was the single?
All of it. So
Yeah.
with telescope, we had this new, I didn't show any videos today, it's new technology of spin casting mirror. You take big pieces of glass, like loaf of bread, and you spread them in that spinning oven. So this oven is that high, there are walls around. You put these pieces of glass, you put lid on the oven, and the oven starts spinning at about 1 turn per minute, and you raise the temperature until glass is melted, and then it's liquid. And then as it rotates, of course, the free surface has to be parabola, and that's exactly what you need for optics. And then you cool it down over a few months, very slowly, and once you take the lid off, you have this beautiful mirror. You need to polish it a little bit outside. Our primary mirror actually is primary and tertiary, so we did need to polish in the middle. But in the end, that mirror, instead of being maybe $100 million with classical technology, it was only $30 million with this spin casting. So that was one technological breakthrough. CCDs were designed to our specs, so they were developed both at ITL in Arizona and E2V from UK. They had to be special thick sensors, back illuminated, with very wide sensitivity range, so that was one technological breakthrough. But I think most of all, it was our ability to handle every night so much complex data. It's much more, I know at CERN saying that you will have 60 petabytes of data, it doesn't sound that much. But we also have very complex data, and we cannot predict all the possible shapes of galaxies and so on. So it is not an easy problem for different reasons than just data volume. It's very complex.
Okay. There was a question there I saw first, and then up there. Yeah.
Hello, thank you for the talk. It's a follow-up question on the satellites. I was wondering, since right now there's already poor mapping of the current satellites that are there, which are already a nuisance.
Could you please get closer to the microphone?
The current satellites that are up there, they are very poorly mapped by the people who have sent them up there. And I was wondering whether, since this is already a nuisance for many telescopes, whether this survey will be able to start such an extensive mapping in the rejection process that you talked about. And similarly, are all the pipeline projects for immediate rejections already complete, or are you still making those currently?
So for most of satellites, you do get orbital elements, so-called TLE, and there are databases, and we use them to predict where the satellites would be. They are not as accurate to predict exactly where the line would be. So what we are doing is we run so-called half transform on each image that picks up anything that is linear feature. It's well used, I think, in this field here. So we pick up all those lines. Later, you can cross-correlate them with the database of satellites, and it's not 100% success, but most of these satellites are already in database. And I'm talking about LEO satellites, low Earth orbit. Now, there are some other satellites that I don't want to talk about, and they also, some of them are cataloged, but eventually, if you are interested in that, all our images to members of collaboration are available within few days. And if you're not in data right holder for Rubin data, after 2 years, everybody in the world gets them. And so then people can do all kinds of analysis. There will be no masked pixels. There will be no missing data. If you're interested in satellites for one reason or the other, you can do whatever you please.
Okay, quick question there, and then I want to go to Zoom for a couple. Yep.
And how much commonality is there between like a telescope and a particle detector? And is there any like exchange of expertise between CERN and your observatory?
There is no direct exchange at formal level, but there are a lot of people who are familiar, especially in HPC, who are familiar with what's being done at CERN and what we need to do. And that comes mostly through our people who are at SLAC, at Brookhaven, at Fermi. And then there are many people on our project who worked on Babar and then switched to Rubin. And so there is a lot of informal interaction, and basically they know about progress on both sides of the fence. But as far as I know, there is no formal agreement of any sort between CERN as an organization and our observatory or our umbrella observatories like Noir Lab. We are part now in operations of Noir Lab, which is U.S. National Observatory. And then there is AURA organization that manages everything, including Space Telescope Science Institute and many other observatories.
And is that why the camera was built at SLAC? Was it because of the Babar? Did it go the other way around?
That was consequent. The reason why it was built at SLAC was the Department of Energy provided major funding for the instrument.
Okay.
So it was shared funding between National Science Foundation and Department of Energy.
Okay. Question on Zoom. How exactly do you measure the redshift? Do you have spectral information on each object? How precise is this information?
Right. So it's basically supervised classification. You have a training sample of galaxies that have spectra, and you get redshift, which is piece of cake, autocorrelation, correlation, so on. That's easy. And then we measure colors. And now if you look at just one color versus redshift, you get some relationship. And often it's not a true function. You get multimodal solutions and so on. But if you had another color, which is based on different wavelengths, you get another function. Or if you want to think in multidimensional space, we have 6 bands, so 5 colors. In this 5-dimensional space, there is this manifold that you travel as you go in redshift, and you are parameterized by redshift. And then you get training sample. You already can do unsupervised classification. You get manifold in color space. And then you take training sample, and you just map positions in that manifold that map onto redshift axis, and that's how you get it.
And the images you showed, the beautiful images, this is an optical camera, but presumably there's image processing going on. How heavy is that? I mean, if you compare it to James Webb, which is heavily processed for us to see it, being infrared.
Right, so you cannot see all the wavelengths. We go from 3,000 angstrom all the way to 10,000 angstrom.
Right, okay, yeah.
So you have to do some false color. Okay. But with GRI, the images I showed, they are pretty much close to human eye. So if your eyes were as big as this room, that's what you could see on the sky, the same colors.
Because there was this one final question on Zoom. Are these and future videos publicly available? They are clearly great for outreach and education.
Yeah, they are all already on our webpage. You just Google Rubin Observatory first look, and you'll get to webpage, and you have all kinds of resolutions and images and videos.
Okay. Question here.
Thank you so much for the talk. the images were one of the most beautiful pictures I've seen of the universe. So my question to you was, this being the largest camera in the world now, there must be thousands of sensors on it. So how do you handle the real-time correction for all of these sensors to avoid the, the crosstalk between these sensors while they take these images?
There is a little bit of crosstalk between sensors on the same raft, that 3x3 thing, and we already measured that in the lab even before camera went to Chile from Stanford. It's quite stable. It's only function of temperature. And so we have lookup tables for crosstalk as a function of temperature, but we also control the temperature of the camera to within few tenths of Kelvin. So it is well stable, and we correct for this a priori. And the rest of it, we calibrate just like any other astronomical observation. It's mostly, what we need to calibrate is mostly atmosphere. That's what changes the property of the whole system. The camera itself is pretty much stable compared to what atmosphere is doing.
Another question here. I think these are the astrophysicists and astronomers on this row, I can tell. Please.
So I have a question regarding what you mentioned before. You mentioned that the picture that won the nicest picture on Nature was actually 20% below the benchmark. Do you know how that came, and did you fix it already? If so, how? And also related to this, what are typical, maybe technical challenges within the operation of the telescope?
You said it wasn't stitched. I didn't quite understand.
I'm sorry. You mentioned before that the picture was actually 20% below the benchmark that you set for the resolution. How did that come, and have you fixed the issue already?
I see. Now I understand the question. So the question is, the image resolution was quite there where it should be regarding the specs. There were two sets of problems. So we need to correct the mirror. As you change the direction of the telescope, that mirror, you should think of it as a Play-Doh, not solid thing. It deforms. Not that you can see with your eye, but it deforms sufficiently much that your image would be totally blurred if you didn't correct. So what we do is we have 180 pistons under the mirror, and they operate at about 10 hertz. So we read out images in these corner sensors very quickly. Then we deform the mirror, and so that makes this shape perfect. The problem is that even if the shape is perfect, there is still air in the observatory, and its turbulence can change the quality of the image. So one problem we had was thermal control, both in the mirror itself. Mirror also have some nozzles where air-conditioned air comes in to keep it steady, and that wasn't properly calibrated. Then on this dome that I showed you, there are these huge louvers that we are supposed to open around 4 or 5 p.m. so that the wind can come in and the temperature can become similar to the outside temperature. Well, dome actually is not finished yet. Only half the louvers are operating. So temperature in the dome is still not quite the same as outside when we start observing. So these two thermal effects are killing us. Then our active optics system, which means we read images of stars, we look at the wavefront, and from the deformation or from the shape of wavefront, we can invert the equations and say what we need to correct in our optical system. And we have 50 degrees of freedom when you take the mirror, 3 mirrors, then you take the camera, hexaputs, and everything else. It's quite complex. And so our software also wasn't fully commissioned. There were even some bugs and so on. So it took us some months to fix these little things to go from 20% problem, we are down to 10% problem. We are still not quite there where we need to be, but we understand what we need to do over the next year or so to get to the full specs. So it's very complex, finicky system. It's fast optical system, f1.2. It's very hard to optimize all of that.
Yes.
Okay. Good.
You mentioned towards the start that you think that this survey will be able to distinguish between the correctness of general relativity and a modified theory of gravity. To what extent are you confident in that statement? And in general, what is the consensus on that?
With about full survey, the claim from simulations is that it will be detection somewhere between 5 and 7 sigma. So statistically, it's convincing. If you have some systematic errors you didn't take into account, maybe it's all like not reliable. That remains to be seen. Basically, what you do is you measure the growth of structure through the galaxy distribution on the sky, through galaxy clusters. It's exponentially sensitive to growth of structure. And then you also measure the expansion of the universe. Then you can construct some dimensionless quantities that don't have direct physical meaning, but you can basically summarize the entire huge data set into that one number. One famous quantity that doesn't have name is E_G. And so in GR, it's predicted to be 0.4. And with SDSS that I mentioned, the result was 0.35 or something, plus minus 0.15. So the error range is enclosing GR. And if you ask for modified gravity theories, where are they? They are like 0.3, 0.32, and so on. So they are different. They are not 0.4. The problem is that the measurement error from SDSS data is larger than the difference between correct GR and wrong GR. What you need to do is to get the data that has this small error bar. And then you ask, is it going to fall here or fall in here? Or if it falls in the middle, then your generation will build a new survey and you'll go further. That's the game we play.
And these modified, I mean, to my knowledge, it's way out of date. I'm thinking MOND and the early galaxy rotation curves. In terms of the robustness of alternative theories of gravity, can you modify, I mean, if LSST found really a 5-7 sigma disagreement with, which shows that GR just, you know, it must be something else. Aren't there there's other observations that have to be accounted for by alternate theories of gravity? I mean, how robust are these alternative models of gravity today? We've moved way beyond the MOND paradigm.
Yeah, good
presumably.
question. I imagine the first step in that reasoning would be that we show inconsistencies with GR, that there are some predictions of GR that we can test robustly. And if it cannot explain observations, then the next step is to ask which modified theories are in the right ballpark. And then most of these modified theories, they are not nearly as deep theory with predictions like GR, because people have many ideas, they try a little bit, there is no motivation today. But if we reach the point where we say GR does not work, we cannot explain what we see, then it will give impetus to theorists to now start exploring in all possible directions.
Yeah.
And in general, you can never prove hypothesis or theory. You can only reject things.
Are there any final questions? I think I see one on Zoom. This is from Louis Lyons, who's one of the most respected statisticians in high-energy particle physics, joining us on Zoom. You were lamenting that you are not yet using Bayesian methods. What priors would you be using, and would you not prefer to do without them?
To do what?
To do without them, to fit.
I was referring in particular to star-galaxy separation.
Okay.
And so that means basically morphological separation. So you have an image. Imagine just a Gaussian image. And most of your images are Gaussian, but some of them are slightly wider Gaussian than most of them. That's a well-posed statistical question. And you can easily write likelihood of that fit. You can do likelihood ratio and so on. In astronomy, that problem comes in the context of very imbalanced samples, where if you look at high galactic latitudes, you can have 100 times more galaxies than stars. If you observe towards galactic plane, you can have 100 times more stars than galaxies. So prior is hugely important. And then the question is, how do we get the prior? And so you can get prior just from this big image that has 10 million galaxies and number of stars. You just look at all of them, and statistically you correct for biases, you get prior. Or you can do even better things. Today, thanks to development over the last 2 decades or so, we understand quite precisely how to compute population synthesis in the Milky Way. We understand how stars are distributed. We don't know all the details about their kinematics. We don't know all the details about their chemistry. But stars in the Milky Way, we can predict to much better than factor of 2, maybe even 10, 20% with models, just counts. And that's what I need for priors. And these priors now, as I said, they have huge dynamic range, going from 1/100 to 100 to 1. And I can predict number of stars in galaxy to within 10, 20%. I'm golden. And then, of course, for galaxies, that's easy peasy because they have this variation due to large-scale structure, which is under factor of 2, and we understand galaxy counts down to deep limit. So we control priors. In this context of morphological star-galaxy separation, or in other words, recognizing that some objects are larger than your resolution of your image. Most stars, they just reflect resolution of your image. If we had infinite resolution, they would be like 1,000 times smaller than what we get from the atmosphere. So they tell us what's the resolution of the instrument, and then we ask, given some signal-to-noise ratio, is this object consistent with being unresolved, or do I see statistical evidence that that object is larger than the resolution of the instrument? But to get statistical posterior probability, you must take prior into account. It plays a role.
Okay, thank you. And you're holding up very well to this barrage of questions. I'll take one more on Zoom before going back to the Astro row. Do I recall correctly that you said that several scientific publications have been written, submitted, on the basis of a few alerts from the preview data? If you get 10 billion alerts and 0.1% lead to interesting discoveries, who will be reading, writing and reading the corresponding papers? It's a lot, basically, right?
Yeah, well, I think eventually we will not be writing papers about single alerts.
Right, okay.
We will be doing population studies and such. And also, most of these alerts, they are not something never seen. Alerts are defined as anything that we see in difference image. But that means we will see just garden variety variable stars, few hundred million and so. We will see asteroids. We will see things that are repeatable, and so we detect everything. The most interesting alerts will be those that we've never seen before. So if you wanted to look for orphan gamma ray burst afterglows, then you say, give me alerts that appeared where nothing ever before appeared. And then, of course, you'll get mostly junk. Then you have to learn how to get junk out, and then eventually you'll get some exciting scientific discoveries. So that's the game we will have to play.
And you'll let us know at CERN if there's an asteroid heading our way.
We will definitely let you know.
So we have time for maybe a couple more here. Yeah. I don't know who was first. You can decide.
So another thing I was wondering is what would be some typical technical challenges in operation for such a big and fast telescope?
The main technical challenge is to keep the efficiency going. Because we are not ordinary observatory where you have time allocation committee and then there is shared risk and sometimes you don't get your data. Our very mission is designed on the premise of efficiency. So we have to keep hardware going, go, keep getting images. At the same time, we also need to have our software being robust. You cannot play around with new version and then kill processing software for that night. So we have many steps of how you get to the production level. And most important of all is how to keep our team excited. After 10 years, whatever comes to your mind that may seem fun to you, after doing it 10 years, it will get boring. So we need to think about how to motivate people, how to keep them alert, how to keep them safe, how to keep them efficient. So there are many challenges in such project. But excellent question.
Okay, yep.
You explained how you constrain priors, but I was wondering how you take biases into account, especially for structure of galaxies, because especially when you look at higher redshifts, you've got formations like fingers of God. Would that be statistically then? And if it is statistically, what database are you using to do that?
In this narrow context of separating stars from galaxies, when you look at what quantities you use, you show that you can use many quantities in the absence of noise. They are one-to-one related. When it comes to noise, that's when you get better and worse star-galaxy separators. And you can show that just measuring flux of an object with two different profiles. One is that inherent instrumental profile that we know from many stars, and then the other one, you allow it to widen to be the best fit to the source. The ratio of those two fluxes is statistically the best way to distinguish resolved from unresolved object. And then if you look now at a sample, you take an image, and you have many objects, hundreds of thousands. When you look at the distribution of this, you will have one very narrow Gaussian for stars, and then you'll have something very wide that looks like log normal distribution that corresponds to galaxies. And then as you go fainter and fainter, stars will start widening due to increasing errors. And this log normal distribution will widen a little bit due to the same effect. It will also come closer to stars because as you go further, galaxies are smaller and smaller. But now you can, in magnitude bins, in flux bins, you can model this distribution. And then you can see how it varies with magnitude, and you can fit some smooth functions. And so while in the case of individual source, you cannot tell much whether it's star or galaxy at the faint end. From the shape of this distribution, you know the ratios, you know the weighting numbers that go with this component and that component. So I know the ratio of stars to galaxies, even though I cannot tell you for each individual object if it's a star or galaxy. There is still this shape that I feel as a mixture of two components, and that tells me my priors directly from image, even if I don't believe galaxy models.
Okay, we're going to end with two questions, one online and one in the room. Online, very quickly, what determines the exposure time of the LSST?
Say again, what?
The exposure time. What determines?
What determines? It
Yeah.
was optimization. If you go much shorter than 30 seconds, then you get problems with turbulence, and your image profile that is not Gaussian. You get this speckle effect.
Okay.
So it had to go longer than this short number. Also, if you go to too short, then readout time becomes important. If you go too long, then you get fewer observations in 10 years. That's not good. And if you go too long, then you get trailing of asteroids, which is not good. So there is this sweet spot between maybe 20 seconds and 60 seconds that is good. Okay. And then we settled for 30 seconds. And just recently, we choose that in U-band, where the sky brightness is very low, and the readout noise then contributes a lot, we said, let's go longer. Let's go to 38 seconds to actually come to the sky brightness limiting case, so we don't care about readout noise. So it was a matter of optimization.
Yeah. Okay, and final question from the room. Thank you.
So just like the operational efficiency that you mentioned, I had another thought in my mind. It was that since Vera Rubin is in Chile, which is, it's in Chile, which is, I'm assuming, close to the South American fault line. Is there something that you have taken into account about seismic activity? Because I imagine since the lenses and the mirrors are so sensitive to, for example, even the air temperatures and deformation, I imagine seismic shifts and then earthquakes, for example, they would for sure maybe play an effect on the image quality. So how is that something that you've considered, and if yes,
right,
how?
We did. Yeah, good question. It's not a new thing for our observatory. There have been observatories for decades in Chile and everywhere else. It's a known problem. So if there is earthquake, it will ruin data, but earthquakes don't last long, so you don't care if you lose 10 minutes of observing time. You care if your observatory collapses. So it was designed to sustain 100-year earthquake, which translates to some Richter scale number, which is standard practice, not just in astronomical observatories, but in any large building that you would construct, like skyscrapers. And then we are designed, if something happens, then there are many subsystems that will go automatically to safe mode. So we hope that nothing will break. We will definitely lose observations, but it will not last long. And there is a lot of experience from other observatories that are in Chile that sometimes suffer from this. So it is something you have to take into account, but it's not a major obstacle.
Okay, I think it's time to give our excellent speaker a break. Thank you for your clarity of your presentation.
Thank you for great questions. It was fun.
And thank you very much. And thanks to everyone for coming, for your questions.